In this video, we're going to look at temperature, heat, and thermal energy. And the main idea is that heat is a transfer of thermal energy that occurs spontaneously from a warmer object to a cooler object. Few essential questions we're going to answer are: how are temperature and thermal energy related? How are thermal equilibrium and temperature related? How is thermal energy transferred? And what is specific heat? This is the very important part, the specific heat. That's the math portion of this video. Few new terms that we might look at are thermal conduction, thermal equilibrium, heat, convection, radiation, and specific heat, and also review the idea of thermal energy. So thermal energy. Like macroscopic objects, particles can have kinetic and potential energy. So we can think of very small particles having this same type of kinetic or potential energy. Gas particles can collide with each other or the walls of their container, resulting in a transfer of this energy. And because there are many particles and many collisions in a sample of gas, it's convenient to discuss the total energy of the molecules and the average energy per molecule. The sum of the particles' energy is called the thermal energy, whereas the average is called the temperature. And so there's a distinct difference between these two. The total energy of all the particles is thermal energy, but the average energy per particle is called the temperature. Say we have a helium-filled balloon and it's kept inflated by repeated pounding from the helium atoms on the balloon wall. And the size and temperature of the balloon are affected by the average kinetic energy of the helium atoms. And if you put that balloon in the sunlight, energy is absorbed from the sun, and it makes each of these helium atoms move faster and faster in random directions and bounce off the rubber walls of the balloon more often, causing the balloon to expand. So when the temperature increases, the average energy increases, so we get an expansion of the balloon. Well, conversely, if we refrigerate the balloon, it shrinks because the particles are moving more slowly, and the refrigeration has removed some of the thermal energy of the helium. The atoms in a solid also have kinetic energy, but they are unable to move freely as they do in a gas sample. One way to illustrate the molecule structure of a solid is to picture the number of atoms that are connected to each other by springs. Because of the springs, the atoms bounce back and forth, with some bouncing more than others. And each atom has a kinetic energy and some potential energy from these springs that are attached to it. And if a solid has n number of atoms, then the total thermal energy in the solid is equal to the average kinetic energy plus the potential energy per atom times n. So that's our number of atoms in a particular solid. Now keep in mind, there are not actually springs attached to the molecules in a solid. However, they do kind of vibrate back and forth as if we had a little mass attached to a spring, and it would be that very similar vibration. And so we consider them to have these spring-like connections. On average, if we have a particle in a hot object, it's going to have more kinetic energy than a particle in a cold object. However, this does not mean that each of the particles that compose of an object has the same amount of energy. The particles that compose an object don't have the same amount of energy. They actually have a very wide range of energy. So you have an object on a table that has a given temperature. Not every particle in that object is going to have the same amount of energy. There's going to be a wide range. Remember, temperature is the average of all the energies. Temperature does not depend on the number of particles in the object. However, the thermal energy of the object does depend on both its temperature and the number of particles, because temperature is average, thermal energy is total. So if we have two muffins, a small muffin, large muffin, they may be at the same temperature, but the large muffin has much more thermal energy than the small muffin does. You've probably used a thermometer before to use temperature, or you at least see thermometers in your everyday life measuring temperature. And the atomic level process involved in measuring temperature involves a collision and energy transfer between the thermometer and its surroundings. When the cold glass tube of the thermometer touches something that is warmer than the glass, the faster moving particles of the surroundings collide with the slower moving particles of the glass. Energy is then transferred from the surroundings to the glass particles by the process of thermal conduction. So anytime we touch, this is conduction, which is the transfer of thermal energy when particles collide. And the thermal energy of the particles that make up the thermometer increase, while at the same time the thermal energy of the particles of the surroundings decreases. Now, the thermal energy is decreasing in the surroundings very slightly because the thermometer is a small object, whereas the surroundings typically are going to be a much bigger object, so you won't necessarily notice that decrease in thermal energy of the surroundings. But we do notice an increase in the thermal energy of the thermometer because the reading changes. And as the particles in the glass gain more energy, they begin to give some of their energy back to the particles of the surroundings. At some point, the rate of transfer of energy between the glass and the surroundings becomes equal. The surroundings and the thermometer are at the same temperature. And at this point, this is the important part, the surroundings and the thermometer are said to reach thermal equilibrium, the state in which the rate of energy flow between two objects is equal and the objects are at the same temperature. Objects with a wide variety of temperatures are present in the universe. We see all sorts of different temperatures in just our everyday life on Earth, and then if we broaden our scope to even space and the entire universe, we see a very wide range of temperatures. Temperatures do not appear to have an upper limit. They can keep going on and on and on, and we see things hotter and hotter and hotter. However, temperatures do have a lower limit, and this is known as absolute zero. At absolute zero, all the thermal energy that can be removed from a substance has been removed, and it is impossible to reduce the temperature any further. This can be no temperature lower than negative 273.15 degrees Celsius. In the United States, most of the time we give our temperature in Fahrenheit. And you also may be familiar with the Celsius scale because a lot of countries do use that. Our neighbors to the north in Canada use Celsius, and you can also see that on a lot of our thermometers and digital signs as you drive down the street. And the freezing point of water at sea level is defined to be 0 degrees Celsius, and the boiling point is defined to be 100 degrees Celsius. So Celsius is based off of water. And so at 0, we freeze. At 100, we boil. And if you notice, there are negative temperatures on the Celsius scale, which suggests a molecule could have negative kinetic energy, which is not possible because we know kinetic energy is always positive. So the solution to this issue is to use a Kelvin scale, where the 0 point of the Kelvin scale is to be defined at absolute zero. So each interval on the scale, that's the Kelvin scale, is equal to 1 degree Celsius. So that means that whatever your temperature is in Celsius, if you just add 273 to it, you get the temperature in Kelvin. Now we're going to bring in the real meat of this video and the idea of heat and a transfer of heat and how it affects thermal energy. The transfer of thermal energy, which occurs spontaneously from a hotter object to a cooler object, is called heat. Heat, like energy and work, is measured in joules, and we use Q to signify heat. And if Q has a negative value, thermal energy has left the object. And if Q has a positive value, then the object has absorbed thermal energy. So we use Q as the idea of the transfer of heat. And if Q is positive, we increase. Q is negative, we decrease. So recall that thermal conduction is the transfer of thermal energy that occurs when particles collide. So conduction is happening when we touch. So, for instance, if we put a frying pan on an electric stove, that heat from the stove is being transferred into the frying pan. And so Q is positive there for the frying pan because heat is being absorbed into the frying pan. There are other ways that we can transfer energy other than just conduction. And heating caused by the motion of fluid in a liquid or gas due to a temperature difference is called convection. An example of this would be heating a pot of water. Thermal energy flows from the rising hot water and the descending cold water. So as you heat the water, we're heating the pot through conduction most likely, if it's sitting on the stove, and then the water is transferring energy within itself through convection. And thunderstorms and hurricanes are example of large-scale convections. This is the movement of air through our atmosphere and changing the temperature. However, radiation is a transfer of energy by electromagnetic waves. And we see this every day when we get energy and heat from the sun. Radiation does not depend on the presence of matter, which is good because otherwise we would not be able to get any of the energy from the sun because the space between the sun and the earth has very little to no matter in it. And the sun warms the earth from more than 150 million kilometers away using radiation. Now, one of the terms that we're going to use here in this unit of thermal physics is specific heat. And this term is very different than what you may be thinking. Now, some objects are easier to heat than others, and you may have found this in your everyday life. You know, you'd see that metal heats up very quickly where water takes a long time to heat. And we call this the specific heat of a material. And so this is a way to quantify that idea, that representation of some objects are easier to heat than others. And so the specific heat of a material is the amount of energy that must be added to the material to raise the temperature a unit of mass by 1 temperature unit. In SI units, specific heat is measured in joule per kilogram Kelvin. So the heat Q required to change the temperature of an object depends on the mass of the object, the change in temperature, and the specific heat of the substance. And so our main equation that we are going to use in this unit is Q equals mc delta T, where delta T is the change in the temperature. So let's look at an example with this. So sometimes a short circuit in an electrical wiring system can produce enough thermal energy to melt a wire. How much thermal energy must be transferred to a 20-gram piece of copper wire to raise it from room temperature, 25 degrees Celsius, to its melting temperature of 1085 degrees Celsius? So if we look at the situation, this is heat going into a wire. We know the mass, the initial temperature, the final temperature, and we look up the specific heat of copper. That'll typically be given to you, or at least you'll have a table that you can look at for the specific heat. So we want to find what is Q. Well, solve for the unknown, we use our equation, Q equals mc delta T. If we plug in all these values, we get 8,162 joules. Now keep in mind, we subtracted these temperatures in Celsius, and I said earlier they need to be in Kelvin. But remember, the difference between 1 degree Celsius and 1 degree Kelvin, they are the same when we're subtracting them, because each unit value is the same in Kelvin and Celsius. It's just the starting points are different. And so we want to check this answer. Does it make sense? Yeah, heat is heat is measured in joules, so the units are correct. And a quick estimate, if we wanted to look at these values without using a calculator, we could see it's going to be about 8,000, which is close to our answer. Looking at another example, we have a 0.025 kilogram block of an unknown substance. And this process that we're about to look at here is actually used a lot of times to identify unknown metals. And so if you have a metal substance and we don't know what it's made of, we can use this process that we're talking about here to discover the components. And so it's at a temperature of 82 degrees Celsius, and it's placed in the calorimeter with 0.025 kilograms of water at 22 degrees Celsius. The system reaches an equilibrium temperature of 27 degrees Celsius. We want to know what is the unknown substance. So there's a heat transfer going on here. So this metal, or whatever the substance is, we don't know if it's a metal or not, but it has some amount of thermal energy, and then it reaches equilibrium with water, which has a much lower temperature, lower average kinetic energy of particles. And so it reaches equilibrium at 27 degrees Celsius, and we want to know, well, what is the specific heat of that object looking at the heat transfer? So heat is going from the unknown substance into the water to reach equilibrium. So what we're looking at here, we have all of our known values, our initial temperature of the water, the mass of the water, the initial temperature of the unknown substance, and the mass of that substance, and they both have the same final temperature. And we have the specific heat of water. Once again, we can look that up, and that's 4,180 joules per kilogram degree Celsius. And so we know the heat transfer from the water is going to equal the heat transfer from the object, the unknown object. And so we set those two equal to each other. The mc delta T equals mc delta T. And so we solve for the C here by dividing the heat of the water by the mass of the unknown object times its temperature difference. And we plug in all of our numbers and we get 380 joules per kilogram degrees Celsius. And so this corresponds with copper. If we look up in a table, we can see that this is the specific heat of copper, so this unknown object is. Hopefully now, after watching this video, you are able to answer these essential questions and have a general idea of these vocabulary terms. Thank you.